In the year 1818, Gauss, who is hailed as the chief mathematician in the history of mathematics, discovered something incredible. At that time, Gauss was responsible for measuring the land of the Duchy of Hanover. He used a method for solving systems of linear equations to measure a large triangle, known as the method of least squares. Gauss found that the sum of the angles in this enormous triangle was greater than 180 degrees. Although it was only slightly more, it was definitely not equal to 180 degrees. Gauss was astonished. How could this be possible? For over 2,000 years, everyone believed that the sum of the angles in a triangle was equal to 180 degrees, a theorem that had been rigorously derived. This measurement shattered a sacred mathematical theorem, revealing flaws in geometry. Gauss had unwittingly entered a space that humanity had never discovered before. In that magical space, the universe transformed into something else. This was a discovery of space by humanity. To understand this wonderful story, we need to start from the beginning. In 240 BC, Eratosthenes, a Greek scholar in Alexandria, Egypt, noticed something unusual. In Siene, now Aswan, at noon on the summer solstice, the sun shone directly on a pillar without casting a shadow. This surprised him because in Alexandria, the sun always cast a shadow. He concluded the earth was spherical. At noon on the solstice, he measured a shadow in Alexandria, forming a 7.2 degree angle. He measured the distance to Siene, about 5,000 stadia, 800 kilometers. Knowing a circle has 360 degrees, he calculated 7.2 degrees. After much contemplation, Eratosthenes concluded that this likely indicated that the Earth was a sphere. On the summer solstice at noon, he measured the shadow of a vertical pole in Alexandria and found that it formed an angle of about 7.2 degrees. He then had someone measure the distance between Alexandria and Siene, which was about 5,000 stadia. A stadia is an ancient Greek unit of measurement, and 5,000 stadia is roughly equal to 800 kilometers. Since a circle has 360 degrees, he calculated that 7.2 degrees over 360 degrees should equal 800 kilometers over the Earth's circumference. Through this calculation, he determined the Earth's circumference to be 40,000 kilometers. Eratosthenes successfully measured the Earth's circumference using simple geometric principles. Today, people use satellites to accurately calculate the Earth's equatorial circumference to be 40,075 kilometers, so Eratosthenes' calculation was already quite accurate. However, in that era, no one believed in the spherical Earth. Another ancient Greek philosopher, Pythagoras, raised objections, saying, "If the Earth is a sphere, what about the people on the bottom? Won't they just fall into space?" From this story, we can derive a question. How can we understand the world we live in? Since the emergence of Homo sapiens, humanity has been exploring what the world is like. Even 2,000 years ago, and even a few hundred years ago, people did not believe that the Earth was a sphere. Humanity had to find a way to explore the world. What is that method? This is a very profound question. To understand the essence of the world, we must develop a special tool, mathematics. Why is it said that only mathematics can help us understand the universe? This question has been discussed in previous programs. I once suggested that the essence of mathematics is the logic of the universe. This may sound a bit convoluted, so we need to first explain what logic is. Simply put, logic is the science of studying correct reasoning and argumentation. Why can't we arrive at correct conclusions without logic? Because only logic can ensure a clear reasoning path between premises and conclusions, ensuring the consistency of reasoning and ultimately ensuring the objectivity of analyzing things. To recognize the essence of things, we need a complete set of methods, which is the method of logic. Similarly, to correctly understand and argue about the universe we inhabit, we also need a complete set of methods, and that method is mathematics. Who opened the door for humanity to understand the universe? We all know that person, Euclid. Euclid lived around 300 BC in Alexandria. He wrote a book that is the second most published in history, after the Bible. We have all studied the content of this book, which is elements. The foundation of elements is very simple. It consists of 5 definitions and 5 postulates. From this foundation, one can derive various propositions in plane geometry, solid geometry, and elementary geometry. This book is one of the most remarkable books in human history. As we mentioned earlier, Eratosthenes was able to measure the Earth's circumference based on the properties of circles and the theorem of similar triangles in geometry. This was humanity's first use of mathematics to explore the world we inhabit. This mathematical tool is geometry. To reveal the infinite and mysterious universe that we will discuss later, Let's quickly review a few postulates. The 5 postulates of geometry are as follows. 1. A straight line can be drawn between any 2 points. 2. A straight line can be extended indefinitely. A straight line can be drawn between any 2 points. A straight line can be extended infinitely. With any point as the origin, you can make a modulus of any radius. All right, angles are equal, and these concepts are quite simple. The so-called postulates are truths that do not require proof. They are universally accepted as correct. However, the 5th postulate is different. It doesn't sound as easy to understand. The 5th postulate states that if a straight line intersects 2 other lines and the interior angles on the same side are less than 90 degrees, then those 2 lines will intersect if extended on that side. What does this mean? It sounds nothing like a postulate. It sounds more like a theorem, something that seems to need to be derived. If the 5th postulate needs to be derived, is it possible to derive it using the first 4 postulates? Ancient Greek mathematicians like Ptolemy and Proclus attempted this, but failed. This has been a problem that has puzzled countless mathematicians for over 2,000 years. The inability to derive it suggests that Euclid was quite rigorous. The fact that the 5th postulate cannot be derived indicates that it is indeed an axiom, something self-evident. But is that really the case? In fact, behind the 5th postulate lies a stunning secret. In 1823, a 20-year-old Hungarian mathematician, János Bolyai, wrote a letter to his father, stating, "I have discovered something so wonderful that I am amazed. I have created a strange new universe from nothing." What did Bolyai discover? He found an interpretation of the 5th postulate that had never been explained before. The 5th postulate can also be understood as stating that through a point outside a line, there is exactly one line that is parallel to that. Therefore, the 5th postulate is also called the parallel postulate. Bolyai discovered that this postulate was not entirely correct. It is only correct until it is proven. In fact, through a point outside a line, there can be infinitely many lines parallel to it. Some might think this is impossible, but that's because we always need problems from a flat perspective. When Bolyai placed the line on a curved surface, this situation emerged. Wait a minute. These lines are not straight. They appear to be curved. That's because the shape of the curve. These curves are still the shortest connections between 2 points, and mathematically, we call such lines geodesics. For example, when we fly from one city to another, we usually fly in a straight line, but when we flatten the spherical space into a 2-dimensional image, it seems like the plane has taken a curved path. This is the result of the change in the shape of space. In fact, today, we know that there is no truly flat space in the world. There are only curves. Bolyai published his findings in 1822, and soon after this work, mathematical investigations reached the mathematician Gauss. Gauss first highly praised Bolyai, considering him a top mathematical genius. However, Gauss then shifted his tone, stating that Bolyai was not the first to discover this. He himself had found the world of surfaces 30 years earlier. Gauss was not exaggerating. This is the story we began with. In 1818, while measuring the land of the Duchy of Hanover, Gauss arrived at results that differed from those of plane geometry, finding that the sum of the angles in a large triangle on the ground was greater than 180 degrees. Gauss was the first to discover that if the sum of the angles in a triangle is 180 degrees, the triangle is in flat space. If the sum is greater than 180 degrees, the triangle is in spherical space. And if the sum is less than 180 degrees, the triangle is in hyperbolic space. Gauss wrote in his mathematical notes that efforts to derive the parallel postulate of the other postulates of Euclidean geometry would fail. Why? Gauss said, because space might be another geometry. Through the study of mathematics, humanity once again questioned the universe we inhabit. Not only Gauss and Bolyai, but also their contemporary Russian mathematician Nikolai Lobachevsky independently discovered the secrets of space. These mathematicians found that when space is spherical, there are no parallel lines in the circumference. This is called elliptic geometry. When space is hyperbolic, there are infinitely many parallel lines through a point outside a line. This is called hyperbolic geometry. Today, we collectively refer to elliptic and hyperbolic geometry as geometry. Once humanity had the appropriate mathematical tools, physical discoveries began to unfold. In 1915, Einstein published the general theory of relativity, pointing out that matter, an energy curved space, and gravity pulls the space around us into a curved shape. The universe is truly amazing. The research of mathematicians like Gauss has actually turned into reality. Indeed, there is curvature in space that follows non-Euclidean geometry, which not only predicts the strange space-time structure around us, he also made predictions about the shape of the universe. So how do we determine what the universe actually looks like? The method is to observe the curvature of the universe. Astronomers have many ways to observe the curvature of the universe, and the basic idea is similar to the triangulation method used by Gauss when measuring the Earth. Look for giant triangular stars in the universe. If the sum of the angles in the triangle is 180 degrees, then the triangle is in flat space. The universe is flat. Current observations suggest our universe is flat, but this isn't the final conclusion, similar to ancient beliefs of a flat Earth. If the sum of the interior angles of a triangle is less than 180 degrees, the triangle is in hyperbolic space, which means that the universe is an open universe. According to current observations, our universe appears to be a flat universe, but this is not the final result. Just like 2,000 years ago, people on Earth believed that they lived on a flat land. Now we think that living in a flat universe is probably because our technology is not yet developed. What else do we need to understand the universe better? That's the theme of today's episode. We need more mathematical knowledge and more insights. The year is 1852, and Swiss mathematician Ludwig Schläfli completed a strange mathematical treatise. The book is titled The Theory of Multiple Continuities. What exactly did Schläfli discover? Draw an equilateral triangle, then a regular tetrahedron, 4 vertices, faces, and 6 edges. Visualize a 5th vertex. First, draw an equilateral triangle on the board, and then use perspective to continue drawing a regular tetrahedron. Even though this regular tetrahedron is on a 2-dimensional plane, we know it has 4 vertices, 4 faces, and 6 edges, with each edge being of equal length. Imagine a 5th vertex. Its distance to the 4 vertices is equal. 10 variations exist. And the distance from this vertex to the other 4 vertices is the same. What kind of shape would this create? It should be drawn like this, in 2 dimensions. We know that this strange trajectory will have 10 variations. It has 10 equilateral triangles, and will produce 5 regular tetrahedra. This shape is called the regular pentatone, which is the multiple continuum described in the previous section. But where do we draw this 5th vertex? It's entirely a product of human imagination. It doesn't exist in the natural world. Schläfli defined a new space outdoors, which led to the concept of a new dimension. This is the 4-dimensional space that everyone is familiar with today. The human visual structure can only observe the 3-dimensional world, which is determined by our physiological structure. Since we live in a 3-dimensional world, our optic nerves have neither the necessity nor the possibility to evolve into a 4-dimensional structure. We cannot observe what a regular polytope looks like in a 4-dimensional world. What should we do? This requires us to change our way of thinking. In a 3-dimensional world, we can project objects onto a plane and observe the shadows of 3-dimensional objects. It's the same principle. We can also shine a light on a 4-dimensional object and let it cast a shadow in the 2-dimensional world. This shape is the projection of the regular pentatope onto a 2-dimensional plane. Imagine cross-sections when a 3D object meets a 2D plane. 2D beings could infer 3D objects by observing these. This shape shows a 3D cross-section of a dodecahedron moving in 3D space. Observing differently helps us envision 4D objects. Schläfli's remarkable thinking set great scientists apart. Similarly, this figure is a 3-dimensional cross-section of the regular pentagon. As it passes through the 3-dimensional world, using different observation methods will help us think about what objects look like in the 4-dimensional world. Having said that, the first person to think about this problem is very remarkable. Schläfli's way of thinking beyond common sense is the difference between great scientists and ordinary people. At this point, our audience might immediately wonder, is it possible that mathematics has once again taken the lead? Could there be higher dimensions in the universe we inhabit? Fast forward to 1919, an unknown mathematician named Theodore Kaluza studied Einstein's general relativity Kaluza was impressed by how Einstein used three-dimensional space and time to describe gravity, achieving great success. What would happen if I added another dimension to space, turning the universe into 4 dimensions? Kaluza was astonished to discover that using the mathematical formulas of general relativity to describe 4-dimensional space not only allowed him to derive gravity, but also led to another set of equations. This formula is what scientists have been using to describe electromagnetic force. So these two forces appear together in one equation. Kaluza sent his research to Einstein. After reading it, Einstein felt quite puzzled. What exactly is this extra dimension? Although Einstein could not explain whether the multidimensional world exists, he was a very open-minded scientist. He helped Kaluza publish his paper at the Prussian Academy, predicting a multidimensional world. A single formula could describe gravity, electromagnetic, strong and weak forces. The multiverse theory is promising, potentially leading to a grand unified theory. Achieving this would be a huge leap for science. Gravity, electromagnetic force, strong nuclear force, and weak nuclear force. This indicates that the theory of the multiverse is very promising, as it could mathematically lead to a grand unified theory. In other words, a universal formula could emerge, allowing us to calculate all known forces in the universe with just one equation. It's truly amazing. If that day ever comes, it would represent a huge leap for human science, comparable in its impact to Newton's publication of the 3 laws of motion. Does the multiverse really exist? Scientists have a hypothesis about this. The universe was 10-dimensional. Its unstable symmetry led to a breakdown, splitting into 4 and 6-dimensional universes. The 4-dimensional one is our macroscopic world. The 6-dimensional universe has been collapsing to 10 more around 32 meters, remaining imperceptible due to technological limits. It then decomposed into a 4-dimensional universe and a 6-dimensional universe. The 4-dimensional universe is easy to understand. It refers to the macroscopic world we currently inhabit. Here, the 4 dimensions are not the 4-dimensional space defined by Schlafly earlier, but rather 3-dimensional space plus 1 time dimension. If we mathematically represent it, it is actually 3-dimensional, which is the universe we currently inhabit. So where is the other 6-dimensional universe? Scientists calculate that the 6-dimensional universe has been collapsing since its inception, continuously shrinking to a size of 10 to the power of negative 32 meters. Today's technology has no equipment capable of observing such a small space, so humanity cannot perceive it at all. However, the macroscopic universe and the microscopic universe have always existed together. In other words, the 6-dimensional universe is right beside us. What does the 6-dimensional universe look like? This is where mathematicians come in to construct it. In 1977, the renowned Chinese mathematician Xing-Tang Yao created a Calabi-Yau manifold. Physicists believe that this 3-dimensional Calabi-Yau manifold is actually a projection of the 6-dimensional universe into the 3-dimensional world. We can perceive what the 6-dimensional universe looks like through this manifold. 6-dimensional universe is everywhere. It is right beside us. Even on the tip of our nose, there is a 6-dimensional universe. But it's too small for us to perceive at all. This is the multidimensional universe that mathematicians describe for us. Of course, the concept of a multiverse is still just a scientific hypothesis. It only exists within mathematical formulas. Historical experience tells us that humanity's physical discoveries about the universe always lag behind mathematics. After Euclid wrote the elements of geometry, Eratosthenes inferred that the Earth is a sphere and calculated its circumference. It was only after mathematicians like Gauss discovered non-Euclidean geometry that Einstein could contemplate the curvature of space and publish his theory of general relativity. Schlafly discovered dimensional space. Does this mean that the universe has higher dimensions? Although humans have not yet discovered a high-dimensional universe, mathematics has pointed us in the right direction. Now, we can answer the question posed in this episode. Why is mathematics always able to predict the universe? That's because mathematics is the most fundamental tool for studying the universe. The essence of mathematics is the logic of the universe. At the end of the program, I want to share a few off-topic thoughts. I used to think that kids below middle school age wouldn't watch my show. Later, I found out that it wasn't that the children didn't watch it, but that many of them didn't have mobile phones or login accounts. They are using their parents' phones and accounts to watch. Some parents leave me messages, hoping I can say a few words to the kids. I advise parents to foster a love for math in their kids. Humanities can wait until kids mature and can discern. Math is foundational and the most remarkable subject. Math helps us understand the universe. Mastering math develops logical thinking. Logic is essential to understanding truth. We can wait until the kids grow up and have the ability to discern before slowly introducing those topics. But math is the foundation of everything. It's the most remarkable subject in all of human knowledge. Only math can help humanity understand the mysterious universe. Mastering math means that kids have the ability to think logically. Why emphasize logic again? Because logic is the only way for us to understand the truth of the world. All right, that's it for today's episode. Don't forget to follow Lau Ming's channel, and we'll chat again in the next episode.